Okay, so to set the stage for Galois theory, I'm going to provide some definitions here. And what I'm trying to do is, again, present this subject to a general audience. So typically, if you were to ask a professor how to go about studying Galois theory, he would normally tell you you need to first study abstract algebra, you need to learn about groups, fields, rings, ideals, a whole bunch of theorems, and this could take several semesters. And typically you would not get to actually learn the ideas of Galois theory until perhaps the end of your undergraduate or beginning of your graduate studies. But what I'm trying to do here is present the ideas to a general audience. I'm going to still be needing some concepts from abstract algebra, but I'm going to use them on an a la carte basis. I'm going to explain them as I go along so that I'm not requiring anyone to know these subjects in advance. So what we saw, so now we're going to talk about a little bit about permutations, the symmetric group, and symmetric polynomials. And so what we saw in the previous example with x squared minus 2, we found that we could actually switch those roots without affecting their algebraic properties. Again, numerically, obviously one root was positive, one was negative, so on a number line you would easily distinguish them. But the key idea is that we were able to switch them without affecting their algebraic properties. We found that any polynomial which satisfied, for which one of the roots was a solution, would also have the other root as a solution. And then any two-variable polynomial would allow, if x and y were, if the two roots were a solution to the two-variable polynomial, then they would also be a solution in the reverse order. Okay, so this simple observation leads us directly to the heart of Galois theory. The idea that you can rearrange, permute the roots of a polynomial in certain ways without affecting the algebraic relations between those roots is at the core of what we know as Galois theory. So I'm going to make a few definitions here. A permutation is a rearrangement of a sequence of letters. So for example, it's kind of like if you have letters in a Scrabble tray and you just write them in a different order. You could start out like this. You could rearrange them like this. So we just simply start out with letters in a certain sequence and we rearrange them any way we please, and that's called a permutation. Okay, the symmetric group in mathematics is the set of all the permutations of n letters. We start with an integer n, here it's 4, we have 4 letters, and we're simply looking at the set of all possible rearrangements of the sequence of those letters. It's written as S sub n, and it has order n factorial. That means there's n factorial different possible permutations of those letters. Why is that? Well, you can take, in this example, we have 4 letters. The first letter, you can just pick any one of the 4. After that, you have, for the second letter, you can take any one of the remaining 3, put that in the second position. For the third letter, you can take either of the remaining 2 and put it in the third position. So you have 4 times 3 times 2 possible choices of how to rearrange those letters. That's equal to 4 factorial. Okay. Now, just a word about the terminology here. When we say symmetric group, and we're going to talk about symmetric polynomials, this is not the ordinary geometric meaning of the word symmetry in the sense that a person's body is symmetric or a snowflake is symmetric or something like that. What we're simply talking about here is a rearrangement, a permutation of a sequence of letters into a different sequence. So it's not like a geometrical symmetry. It's a permutational, and that's honestly a bit of a misnomer. I mean, it really should be called the permutation group, or and when we get to symmetric polynomials, you know, the permutable polynomials or something like that. But this terminology is too well established to change it for this talk, so I'm just going to use these words. These are very standard in the mathematical literature. But just please, do bear in mind we're not talking about geometrical symmetry. We're just talking about permutations here. Okay. Symmetric polynomials are multivariate polynomials. Now we mentioned earlier that polynomials can have multiple variables. You could just have a univariate polynomial, which is what we're really interested in looking at. But in the course of studying univariate polynomials, we're going to be looking also at multivariate polynomials involving any number of variables, x, y, x, y, z, w, x, y, z, and so forth. A symmetric polynomial is a multivariate polynomial for which the variables can be permuted in any way without affecting the expression. Okay, so for example, what are some examples of symmetric polynomials? In two variables, x plus y. X plus y, you can rearrange x and y, you can permute x and y. There's only one permutation when you're talking about two letters, so if you just rearrange it, it becomes y plus x. And since addition is commutative, that's the same thing as x plus y. That's a symmetric polynomial in two variables. Ditto for xy, again, multiplication is commutative. You can switch those two variables to make it yx, and it's still the same thing. So these are symmetric polynomials in two variables, and they have the property that switching those variables does not affect the expression. It's just the same thing. In three variables, you can imagine we also have x plus y plus z, x, y, z, and then we have a more interesting one here in three variables, xy plus xz plus yz. This one's a little bit more interesting, but you can see that if you, let's just say we permute the variables here. Well, let's just say we interchange x and y. Well, this term stays the same, xy and yx the same thing. This changes to yz, and this changes to xz. But then again, we still have the same thing because we've just basically interchanged these two terms here. So again, interchanging x and y does not change this expression. And then you can also do something called a cyclic permutation when we get into three variables. And you can also check that, for example, if you substitute x for y and y for z and z for x, again, you haven't affected this expression. It's still going to be the same thing. So these are examples of symmetric polynomials in two variables and three variables. They happen to be what are called elementary symmetric polynomials. We can talk more of that in a minute. Examples of polynomials that are not symmetric, x plus 2y. Well, you interchange y and x, you get y plus 2x. That is not the same thing as x plus 2y. Again, x squared y, if you interchange x and y, you get y squared x. That is not the same thing as x squared y. So these are examples of polynomials that are not symmetric in two variables. Okay, we've talked about permutations, we've talked about the symmetric group. By the way, it's called a group just because there is also this structure of composition of permutations. And that's not too important for our present purposes, but you can just realize that this is a group, this is just a set basically for our present purposes. Okay, so we've talked about symmetric polynomials. Now, we're going to talk about something called Vieta relations, which I'm going to call symmetric relations. This is actually my terminology. I don't know that I've seen this in the literature anywhere, but this is a way of Vieta relations are relations between the roots of a polynomial, which are formed from what are called the elementary symmetric polynomials, of which we've given some examples here. And they relate the coefficients of those polynomials to the roots using these elementary symmetric polynomials. Okay, so we're going to explain that in a little bit more detail here. We'll give some examples of Vieta relations next. Okay, so again, we're going to start now with the generic second degree polynomial, f of x equals x squared plus c1x plus c0. These two numbers are again called the coefficients, and I'll have more to say about coefficients in a little bit. We're going to assume that these coefficients are integers. It has the two roots r1 and r2, which are of course not integers. We're assuming these polynomials are going to be irreducible. I think I forgot to mention that, but we're assuming these polynomials are irreducible, that is, do not factor over the integers. We'll explain that a little bit more later. Right now I'm just illustrating the Vieta relations. Okay, so f of x factors as x minus r1, x minus r2 when we allow ourselves to look at non-integers. Again, these roots are not going to be integers. The coefficients are integers. The roots will not be integers. And another way to write that is, if we write that out, we get this expression here, x squared minus r1 plus r2x plus r1, r2. And now we can notice that if we simply compare this with the original polynomial, we have r1 plus r2 equals minus c1, and r1, r2 equals c0. So, what we've done here is we've created a connection between the roots and the coefficients of the polynomial, and that connection happens to use these elementary symmetric polynomials which we mentioned in the previous on the previous page. Okay. So this is for a second degree polynomial, and this is generic for any second degree polynomial. We have these algebraic relations between the roots. Algebraic, again, is a synonym for polynomial, meaning we just have a polynomial expression in these two roots which evaluates to these respective coefficients. Okay, in degree 3, same idea, a little bit more involved, but again, we just have a third degree polynomial, x cubed plus c2x squared plus c1x plus c0. The roots, now we have 3 roots of this polynomial. We can write out f of x, we can factorize it this way, and multiply everything out, and then compare the results with the original polynomial. We find that r1 plus r2 plus r3 equals minus c2. r1 r2 plus r1 r3 plus r2 r3 equals c1, that coefficient. r1 r2 r3 is minus c0. So what we've done again, created a connection between the roots and the coefficients using what we call elementary symmetric polynomials, which we illustrated on the previous chart. So these are the vieta, and of course we can go into higher degrees, but that would just involve more, more calculation.